So, if you're listening to this, you are probably pretty tired of AI feeling like, well, a highly rigid game of fetch.
Oh, yeah. Constantly trying to get the prompt exactly right.
Right. For the longest time, you'd throw the stick like a highly specific, perfectly formatted command, and the machine brings it back.
Yeah.
But you throw it even slightly wrong, the computer just, stares at you.
Dying cursor. Yeah.
Exactly. And then generative AI came along, and suddenly it was like having this brilliantly well-read parrot locked inside a dark box. You slide a question under the door, and it slides a brilliant essay back.
Which was amazing at first. I mean, truly.
Wow, totally amazing. But it's still just a text box. It can't see the room, it can't open the door, and it certainly can't, run errands for you. And honestly, you don't want a text box anymore. You want a tool that actually does things.
Which is really the fundamental shift happening in the industry right now. We're moving away from the smart text box paradigm and trying to build systems that can, actually interface with the real world.
And that brings us to our deep dive today. So, on the desk, we have two sources that map out this exact transition. The first is a foundational snippet from the Architecting Intelligence, State-of-the-Art Generative AI Foundation series.
A really solid primer.
Yeah. And then the second is our main course, a highly detailed technical release document from the Qwen team outlining their brand new model, Qwen3.5.
Which is a massive release.
It really is. So our mission today is to cut through all the technical jargon and figure out how we're officially moving to an AI that acts as a native multimodal agent. And, more importantly, how the developers managed to build this thing without completely breaking the bank on computing power.
Yeah, because the computing power aspect is, well, it's the linchpin of all of this. Before an AI can solve complex, real-world problems, it has to be built in a way that is mathematically and, frankly, economically viable.
Right, because if it costs a fortune just to run it.
Exactly. If it takes a $100 million supercomputer a full week just to figure out how to book a flight for you, the technology is useless in everyday life. So efficiency has to come first.
Okay, let's unpack this. Let's start right at the foundation, the architecture. The source document introduces us to a model with a very specific, honestly somewhat intimidating name. It's Qwen3.5 397B A17B.
Yeah, it's quite a mouthful.
Seriously.
Yeah.
But those numbers tell a really interesting story about, the illusion of size.
They do, and
Yeah.
they hold the secret to the model's efficiency. So the first part, the 397B, means the model has a staggering 397 billion total parameters.
Wow, okay.
Right, and parameters are essentially the artificial synaptic connections that hold all of the model's knowledge and logic. But the second part, the A17B, that's where the magic happens.
The active part.
Exactly. It stands for active 17 billion. It means out of those 397 billion parameters, only 17 billion are actually activated during any single forward pass.
Forward pass meaning.
The computational journey the AI takes from, receiving your prompt to generating a response.
Okay, I have to push back here for a second. Wait. If we're only activating 17 billion out of, nearly 400 billion parameters, aren't we essentially just running a smaller 17 billion parameter model?
It sounds like that, yeah.
Right. Doesn't that mean it fundamentally can't hold as much context at once compared to those massive 1 trillion parameter behemoths where everything is turned on? If you're leaving most of the brain off, how does it not lose the broader context?
It's a great question. What's fascinating here is that it comes down to a routing system known as a sparse mixture of experts, or MoE.
Okay, mixture of experts.
Think of the 397 billion parameters as an absolutely massive, sprawling library containing every book ever written. When you walk in to ask a question about, say, quantum physics, you don't need the librarian to turn on the lights in the cooking section.
Or the fiction section.
Exactly. The MoE acts as a highly intelligent router that instantly identifies exactly which expert sections of the library are needed for your specific prompt, and it only wakes them up.
So the knowledge is still all there.
The knowledge is there, yes, but you aren't paying the electricity bill to light up the whole building every single time you ask a single question.
So it's like having a massive 397 billion book library, but you only turn on the lights in the specific 17 billion book aisle you actually need.
That's spot on. And it pairs that routing system with something called linear attention. Specifically, they use gated delta networks.
Okay, let's translate that. What does linear attention actually do in plain English?
Well, in older architectures, the AI used standard attention mechanisms. That meant it had to mathematically cross-reference every single word it was generating with every single word it had already read in a document simultaneously.
Which sounds exhausting.
It is. If you feed it a long document, that cross-referencing gets exponentially heavier. It takes massive computing power. But linear attention changes that.
Oh, so.
It allows the AI to process information more like a human reading a book. It flows sequentially, it updates its memory as it goes along, rather than trying to hold like every single word in its active vision at the exact same time.
Oh, wow. So it's streamlining the actual process of reading.
Yeah. And add to that the fact that they built a native FP8 pipeline. Without getting too bogged down, FP8 stands for floating point 8.
Right, I've seen that term.
It's a lower precision data format. So think of it like doing complex math with rounded numbers instead of calculating out to, 10 decimal places.
Okay, so it's faster.
Way faster. They've designed the algorithm so they can do the math significantly faster and take up half the activation memory without losing the big picture accuracy of the final answer.
Yeah, and the performance data backs this up. Looking at the source, despite only running 17 billion parameters at a time, it matches the capability of models with over 1 trillion parameters, like the Qwen3 Max base.
Which is just wild.
It really is.
Yeah.
But because of everything you just mentioned, the sparse MOE, the linear attention, the FP8 rounded math, it decodes 8.6 to 19 times faster.
19 times faster is the difference between a brisk walk and a bullet train. I mean, they decoupled the parallelism strategies, so vision data and language data don't create bottlenecks for each other. They aren't losing smarts. They are just systematically eliminating the inefficiency of uniform processing approaches.
It's incredible that we have this lightning-fast, highly economical brain now. But navigating the real world requires more than just processing text cheaply. The whole reason this intense efficiency matters is that it frees up the computational budget for the AI to actually see and act.
Which brings us to the concept of the native multimodal agent. Qwen3.5 isn't just a text engine with a camera bolted onto it as an afterthought.
Right, it's native.
Exactly. It's a native vision language model, meaning it was trained from the ground up to understand pixels and text simultaneously as a single cohesive language, and it boasts a context window of up to 1 million tokens.
Okay, to put 1 million tokens into perspective for you listening, that means you could feed this AI up to 2 hours of continuous video all at once.
A whole movie, basically.
Yeah, and it can remember, analyze, and synthesize all of it in a single prompt.
Having that level of visual memory allows the AI to act as a GUI agent, a graphical user interface agent.
Meaning it can click around on your computer.
Exactly. It can look at your computer monitor or your smartphone screen, understand what it's seeing just like a human would, and autonomously navigate complex workflows. The source document goes into detail about something called vibe coding with Qwen code.
Vibe coding, I love that term.
That's so cool. It's a process where you give the AI natural language instructions. You say something like, make me a website that feels like a retro 80s arcade.
Right.
The AI turns those instructions into real-time UI code, but because it has native vision, it actually looks at the visual output it just created.
Oh, so it checks its own work.
Yeah, and it iterates with you visually, tweaking the layout based on the vibe rather than just looking at dry lines of code.
Here's where it gets really interesting, though. Where the model's visual reasoning truly shines, and where the sources get into some fascinating territory, is in the specific real-world examples.
The benchmarks are wild.
Yeah, let's look at the traffic light scenario. The developers feed the AI a dash cam video of a car running an amber light at a busy intersection. Now, typically, an AI doing image recognition would just tag the objects, right?
Yeah.
Like car, yellow light, intersection.
Or it might apply a really basic rule and say, the car ran a yellow light. That is a traffic violation.
Right. But Qwen3.5 goes several layers deeper. It analyzes the frames and actually deduces the physical physics of the moment.
It's amazing.
It recognizes that as the light turned amber, the car was already crossing an advanced stop line marked with a bicycle symbol.
Yeah.
So the AI logically concludes that if the driver had slammed on the brakes at that specific distance and speed, it would have stopped in the middle of the intersection or, caused a rear-end collision.
It understands the point of no return exception to the traffic rule.
Exactly. It is deducing intent, physics, and safety implications from a flat 2D video.
And that requires an understanding of how objects move through space and time, not just what they look like.
Then there's the maze example, which honestly blew my mind. They give the AI an image of a complex black and white maze. Red ball at the start, green ball at the finish.
Right, a standard visual puzzle.
But it didn't just trace a wobbly line using image manipulation. The AI actively pulled up a code interpreter and translated that visual image into a mathematical 21 by 21 grid.
It mapped it out.
Yeah, it calculated that each individual cell in the maze was exactly 28 pixels wide. Then it ran a breadth-first search algorithm to calculate exactly 99-step shortest path from the red ball to the green ball. And then it successfully rendered a perfect red line over the original image to show its work.
It took a visual puzzle, transformed it into a programmable mathematical environment, solved the environment using logic, and then translated the solution back into a visual format.
But wait, let's look at the rush hour parking lot puzzle from the document. The AI looks at an image of a congested parking lot and is asked the question, what is the minimum number of gray vehicles that need to move so the black car can exit?
Oh, the classic sliding block logic puzzle.
Exactly. The AI systematically maps the entire 6x6 grid in its head. It identifies a vertical bus blocking the exit. It realizes the bus must move down. But to move down, a horizontal bus below it must move left.
It cascades.
Right, which means a vertical car next to that must move up, which means a vertical truck must move up. It deduces a precise multi-step dependency chain and answers that exactly 4 specific gray vehicles must move in a highly precise order.
It's mapping the dependencies perfectly.
But I have to ask, isn't this fundamentally different from an AI just predicting the next word in a sentence? We always hear that large language models are basically just super-powered autocorrects. How does predicting the next word allow a machine to look at a picture of a parking lot and play a multi-step logic puzzle?
It is fundamentally different, yes, and the autocorrect analogy really breaks down when we enter this territory. What the model is demonstrating here is the textbook definition of spatial intelligence.
Spatial intelligence.
The AI isn't just matching patterns of text, it is integrating pixel-level spatial relationships.
Like knowing the difference between up, down, left, right, and blocked.
Exactly that.
Yeah.
There is another simple but profound example in the source where the AI looks at a busy street scene and is asked about the position of a red telephone booth. It doesn't just identify the booth.
Right.
It scans the environment, locates a specific yellow van, compares their coordinates in the image, and confidently states that the telephone booth is to the right of the yellow van.
Oh, wow.
By combining that spatial awareness with an understanding of physical constraints, like the fact that a car cannot move through another car, the model performs actual multi-step logical reasoning. It's a massive leap over previous generation vision models that simply labeled the contents of an image like a grocery list.
It's incredible that it can navigate a visual maze or a desktop computer interface like
Yeah.
that. But, navigating the real world also means interacting with human systems. And human systems are built on thousands of different languages, dialects, and cultural nuances.
Very true.
If this technology is going to act as a truly global digital agent navigating the world's systems, it can't just operate in English and Chinese.
Which leads us to the massive linguistic expansion detailed in the Qwen3.5 document. The developers expanded the model's native language and dialect support from a 119 to an incredible 201 languages.
And what really stood out to me was the specific focus on low-resource languages. They aren't just adding French, Spanish, and German. They are intentionally adding languages like Scottish Gaelic, Metis, Kabyle, Zulu, Fijian, and Crimean Tatar.
It's a very clear push toward global AI equity.
Definitely.
Yeah.
But in the document, they also mentioned expanding the model's vocabulary from 150,000 to 250,000 words. So what does this all mean for the end user? Why does adding 100,000 words to its internal dictionary matter? Didn't the model already know how to process these words by just sounding out the letters?
This raises an important question about how AI processes text. It comes down to the mechanics of tokenization. An AI doesn't read letters like we do, it reads tokens. You can think of a token somewhat like a syllable. If a model has a small vocabulary, it doesn't have a specific token for a complex word in, say, Scottish Gaelic. So it has to break that word down into many tiny, inefficient tokens.
Like sounding it out syllable by painful syllable.
Exactly. So it's having to use 5 or 6 computational breaths just to say one single word.
Which takes a lot of processing power.
And costs a lot of money in compute time. By expanding the vocabulary to 250,000 tokens, the AI just recognizes the whole word instantly. The document notes that this larger vocabulary boosts the model's encoding and decoding efficiency by 10% to 60% across most languages.
That is a massive jump in efficiency.
It really is. It means the AI uses significantly fewer tokens to process underrepresented languages. For the end user, whether they are in Fiji or Scotland, this directly translates to much faster response times and significantly cheaper operational costs.
It democratizes the speed and affordability of the tool.
Absolutely.
Okay, so we've established that we have the pieces. The model is highly efficient, it has deep spatial intelligence to solve visual problems, and it speaks 201 languages fluently. But how do you take those pieces and actually train a system to be an independent agent? We keep using the word agent, but what is the ultimate end game for all of this technology?
Well, the capabilities we've been discussing don't just magically appear by feeding the model more data from the internet. According to the source, these performance gains stem from a massive scaling up of reinforcement learning, or RL, environments.
Right, and reinforcement learning is essentially trial and error with a reward system, right?
Yeah.
The AI tries to solve a problem, and if it gets it right, it gets a digital treat.
Broadly speaking, yes.
Yeah.
But crucially, the developers didn't just optimize for narrow benchmark metrics so the model could get high scores on standardized tests. They focused on making the RL environments much harder, much more complex, and more generalizable to the real world.
Okay.
To do this, they built a scalable asynchronous RL framework.
Okay, let's break down asynchronous. What does an asynchronous framework actually mean in this context?
An asynchronous framework means the AI doesn't have to wait in a single file line to process tasks. In older systems, an AI had to finish step 1 before it could even look at step 2.
Right, it was very linear.
Exactly. Asynchronous means the AI can multitask. It can be actively searching the web for the price of a flight on one thread while simultaneously writing the Python code to book that flight on another thread.
Oh, wow.
It doesn't have to wait for one operation to finish to begin thinking about the next. That multitasking capability natively supports what they call agentic workflows.
Agentic workflows, meaning it can handle multi-turn interactions without system interruptions. It can hit a roadblock, try a different tool, search a different database, and correct its own code on the fly.
Yes, precisely.
Let me try an analogy here to see if I'm grasping the scale of this. So it sounds like we're moving away from an AI acting like a short-order cook. You know, someone who just makes the exact meal you prompt them for, hands it to you, and then blanks out waiting for the next ticket.
Right.
We are moving toward an AI acting like an executive assistant, someone you can hand a complex 3-day project to, and you just trust them to manage their own time, use the right tools, and navigate problems on their own to get it done within a budget.
If we connect this to the bigger picture in the summary and future work section of the document, that is exactly the transition taking place. The goal of the AI industry is no longer just making models bigger. The focus has shifted entirely to system integration.
System integration,
Yeah.
building the infrastructure for the AI to actually live and work in.
Exactly. They are building agents with persistent memory for cross-session learning, meaning the AI remembers the nuances of what you worked on together yesterday and the week before that.
It actually knows you.
Yeah. They are building embodied interfaces for real-world interaction, self-directed improvement mechanisms where the AI actively studies its own failures, and something they specifically refer to as economic awareness.
Economic awareness, meaning the AI understands that compute power and cloud services cost actual money, and it needs to solve your problem efficiently to stay within a budget.
Yes. And to achieve a multi-day task with economic awareness, the system's decoupled design that we talked about earlier is absolutely vital.
How so?
When an agent is working on a complex problem for 3 days straight, it generates and consumes massive amounts of data. In older systems, the AI's logic would start to degrade over long workflows because it would get overwhelmed by its own data. That's a problem in machine learning known as gradient staleness.
Basically, the AI starts losing the plot the longer it works on something.
Exactly.
Yeah.
It forgets early constraints or gets stuck in a loop. By tightly co-designing the hardware system and the software algorithms to be decoupled, they can mathematically bound that staleness. The framework can accommodate what they call a million-scale agent scaffold, without the AI's logic degrading over multi-day, multi-step workflows.
So the ultimate goal outlined here is transforming AI from a task-bound assistant that just answers trivia questions into a persistent, trustworthy partner capable of executing complex multi-day objectives.
That is the stated end game for Qwen3.5, yeah. It's the foundation they are building right now.
Well, let's bring this all together for you listening. Our deep dive today shows us that the future of being well-informed about AI isn't just about looking at massive total parameter counts anymore. A 397 billion parameter model is only as good as the 17 billion active parameters routing the logic.
Efficiency is the new intelligence.
It's about active parameters, spatial reasoning, token efficiency that democratizes global languages, and a massive architectural shift toward independent digital agents. The relevance to you is that the tools you will use tomorrow or even later today won't just summarize documents. They're going to take over complex, multi-day workflows, starting right now with things like UI automation, visual puzzle solving, and vibe coding. We have built an AI that can see the pieces on the board, and it actually knows how to move them.
The foundation has absolutely been laid for persistent, autonomous logic.
Which leaves us with a rather provocative final thought to mull over. The source document explicitly mentioned the ultimate goal as an agent with economic awareness capable of executing autonomous multi-day objectives. Imagine a scenario in the very near future. What happens when two different multimodal AI agents, representing two different competing companies, are instructed to negotiate a complex supply chain contract with each other over the course of a week?
Oh, wow. It raises fascinating questions about agency.
Right. If both of these agents have persistent memory, self-directed improvement, and a deep economic awareness of what things cost, who is really making the final business decisions? Have we just built the ultimate negotiating machine, or have we fully outsourced corporate strategy to an asynchronous algorithm?
That is the real question.
We went from an AI that was a parrot in a dark box playing fetch to an AI that might just autonomously buy the pet store. Something to think about. Thank you for joining us on this deep dive. We'll see you next time.